Welcome back, everybody.
We're no strangers to love.
Did I get you? Happy April Fools. Don't forget, after this video, you have a quiz, 5 questions, like before. If you've got questions, let me know. Or come back to the video and rewatch it to look for the answer. Also, you have a Delta Math assignment. It's 5 questions as well. But if you miss a problem, if you get one wrong, you lose a point. So if you answer all 5 correct, you're good, 5 out of 5. If you answer 4 correct and then you get the 5th one wrong, now you got to answer 2 more to get 5 out of 5. So if you get a little bit confused, just let me know. Alright, now back to the lesson. Last lesson we talked about the compound probability of independent events. This time we're going to be talking about the compound probability of dependent events. So the first thing, we need to know the difference between independent and dependent events. So we said independent events were events whose outcomes did not affect the next outcome. So flipping a coin, the first time, regardless if you get heads or tails, it doesn't change the probability of the second flip, doesn't change the probability of the third flip. Now we're talking about dependent probability. So dependent events are going to be events whose outcome do affect the next outcome. One of the most common ways of talking about dependent events, and you'll see examples like these on the Delta Math assignment, is taking marbles out of a bag. So if you have a bag of marbles and you take out one marble at a time, and we're talking about the probabilities, you have 2 options. You can either put the marble back in the bag, that's called with replacement, or you can take it out of the bag and leave it out of the bag for the second time, that's called without replacement. So if you have a bag of marbles and you take one marble out and you do it with replacement, which means you put the marble back in before you pick a second marble, then with replacement, we're going to be dealing with independent events, okay? Because every time you pick a marble out of the bag, you have the same probability as the time before, because it's the same number of marbles and the same of each type of color, whatever the problem gives you. That's with replacement. Without replacement, that means you take the marble out of the bag and you do not put it in the bag before you pick up the next one. So that means the first pick, whatever color you get, is going to change the probability of the second pick. Because there's going to be less marbles in the bag than the first time. Because you're not putting it back in. So without replacement is dependent events. Because without replacement, you're changing the probability the second time. The first outcome is affecting the second outcome. With replacement, you put the marble back in the bag. Each pick is going to have the same probability. They're not going to change because you're not changing the number of marbles in the bag. Without replacement, you are, so that becomes dependent events. So when we're talking about probability, one of the ways that we can find the probability is using what's called a tree diagram. So a tree diagram shows all of the different possible outcomes, and it really helps us, especially when we're dealing with dependent events. So the way that it would work, so this is just a very generic one, we're going to go into some examples in just a second. It shows where can you possibly end up. So when you start, you may have, this example is just showing 2 outcomes, but you may have more than 2 outcomes. So it's saying you could possibly get this outcome, or you could possibly get this outcome. And usually on the branches, we would write what the probability is. Okay, so let's say we had a 1/2 chance of getting outcome 1 or outcome 2. We would write the probability there. Now, depending on which outcome we get, that can change. If they're dependent events, it will affect the second outcome, which are the ones that I have here. So if outcome 1 happens, now we have 2 other options. Now it could possibly be outcome 3 or outcome 4. If outcome 2 happens and not outcome 1, then it could possibly be one of these 2. So this is just a very good way to organize everything where you can quickly find the probabilities, and I'm going to show you how to do that in the first example. So for this first example, I'm going to be using this container with these pegs in here. So I have a container, I have 4 red pegs, 3 green pegs, and 2 blue pegs. So that's a total of 4 plus 3 is 7 plus 2 is 9. So I have a total of 9 pegs, 4 red, 3 green, 2 blue. Now I'm going to offer to play a game with you. So here's the game. Using these pegs in this container, you're going to reach in, mix them up, close your eyes, mix them up, and pick one at random. So you pick one peg, okay? Then without replacing it, so I'm going to put it to the side, I'm not putting it back in, so now there's one less peg. You close your eyes, you mix them up, and you pick another peg, okay? So in this example that I just did right here, I got 2 red pegs. Now, in order to win the game, you have to get 2 of the same color like I just did. So if you get 2 red, you win. If you get 2 green, you win. Or if you get 2 blues, you win. Okay? If you get one of 2 different colors, so if you get blue and green, or blue and red, or green and red, then you lose. Now, I'm offering you to play this game. If you have to pay $5 to play. Okay, so it's a little bit expensive, but if you win, I will pay you $10. So you have the potential of leaving here with twice as much than you started with. So what we're going to do is we're going to use a tree diagram. I'm going to show you how it works, and we're going to find the probability of winning this game. What is the probability of reaching in here at random and picking 2 of the same color? Okay? Now, before we find the probability, I want you to answer this question to yourself. You can write it down if you want, or you can just answer it in your head. But would you play this game? Remember, it costs $5 to play. If you win, you get $10. So do you want to play? And I want you to think why or why not. Why? What is your reasoning for why you would want to play the game? Or if you said no, you don't want to play, why don't you want to play the game? Now, to find the probability of winning, I'm going to create a tree diagram. Now, in the tree diagram, we have 3 options on the first pick, right? So when I reach into this container, the first time I have 3 options. I'm either going to get a red peg, a blue peg, or a green peg. Those are my 3 options. So the first pick, I'm going to have 3 branches. One will be getting a red peg. One will be getting a green peg. And the third one will be getting a blue peg. So those are my 3 options to start off with. On each of the branches, I'm going to write what the probability of getting each of those on the first pick would be. I have a total of 9 pegs. Okay? How many of those 9 pegs are red? There were 4 red pegs out of 9 total. So 4 out of 9 is my probability of getting a red peg on the first pick. What was my probability of getting a green peg on the first pick? Well, there were 3 green pegs out of 9 total. So my probability of getting a green peg is 3 out of 9. And for blue, there were 2 blue pegs out of 9. So my probability will be 2 out of 9. So this first part of the tree diagram represents the first pick. Now remember, we said that we were going to play this game without replacement. That means after we pick a peg, it does not go back into the container. We start over, there's 1 less peg. So if we got a red peg the first time, what are our options for the second time? Well, it's the same 3 options. If we got a red the first time, now we can get a red peg the second time. We could get a green peg the second time. Or we could get a blue peg the second time. Okay? And that's what it's going to look like for each of these outcomes. We could get red and then red. We could get red and then green, red and then blue. Those are the possible outcomes. And it's going to be the same for all 3. So for each of these, regardless of what we got the first time, we have the same 3 outcomes the second time. We could get red and then red, red and then green, red and then blue. We could get green and then red, green and then green, green and then blue, blue and then red, blue and then green and then blue and then blue. Now, if I already picked a red peg the first time, what would be my chances of getting a red the second time? Well, the first time there were 4 reds out of 9 total. Well, now we already picked 1 red and we took it out. So now there's 1 less red. Now there's 3 reds. And there's 1 less peg total. So now there's 3 out of 8 pegs. So now we only have a 3 out of 8 chance of getting a red. For green, since we took the red out, there's still 3 greens in the container, but there's only 8 total. And for blue, there's still 2 blues left out of 8 total. So our probability for this branch will look like that. If we picked a green the first time, there's still going to be 4 reds out of 8. Green, there's going to be 1 less. So we originally had 3 out of 9. Now we're going to have 2 out of 8. There's 1 less green because we already picked it up. We did not put it back in. And so there's 1 less peg total. That's why we go down to 8. And there's 1 less green, so we went down to 2. And for blue, there's still 2 blues because we only took out a green. But there's 1 less total, so it's 2 out of 8. If we picked a blue peg the first time, well, there's still going to be 4 reds out of 8 total left. If we pick, there's still going to be 3 greens out of 8 total left. And now there's going to be 1 less blue. So now there's only 1 blue out of 8 total. So those would be our probabilities for the second pick. So the probability of the second pick, it is affected by the first pick. That's why these are dependent events. There's less pegs than what we started with. Now, to win the game, we said that we had to get 2 of the same. So we either need red, red, so we have to go through this branch, green, green, right here, or blue, blue, right here. So those are our 3 options. But we want to know the probability of getting 2 of the same color. So to find the probability for each branch, each outcome, out of there's 9 total combinations, we have to multiply their 2 probabilities together. So we can do 4 9ths times 3 8ths, and so on for each branch. Now, when you multiply fractions, all you have to do is multiply the tops together and the bottoms together. Now, every single branch has 9 on the bottom for the first pick and 8 on the bottom for the second pick. So I know that every single one of these fractions is going to have 9 times 8, which is 72 on the bottom. To get the number on the top, we just have to multiply straight across. So let's go ahead and do the first 3. So if I want to get red and then red, I have 4 times 3, which is 12. So I have 12 over 72. If I wanted to get red and then green, 4 times 3, that's also 12. And then 4 times 2 is 8, for if I get red and then blue. Now, seeing these as fractions isn't going to help me that much. So I'm going to change them all into decimals so that we can really see which ones are more likely and which ones are less likely. So here are all of the probabilities as decimals. I'm going to write them as percentages as well. Now, one thing you may notice is that these are the percentages of all the different possible outcomes of playing this game. We would have a 17% chance of getting red and then red, a 17% chance of getting red and then green, and so on. Now, to win the game, there are 3 of these that we're really interested in. Okay, so the 3 that we're interested in are the ones where the 2 colors are the same. So red and then red, so that's 17. Green and then green, that was 8%, and then blue, which was 3%. Those are the 3 that we're interested in because those 3 are the ones that will mean that we won the game. So our total percentage, which is 17 plus 8 plus 3, which gives us a total 17 plus 8 is 25. 25 plus 3 is 28%. So to win this game, the probability of winning this game is a 28% probability. So now that you know that you have a 28% chance of winning this game, remember, it costs $5 to play the game, and if you win, you get $10. So now I want to ask you, do you change your answer to what we asked before? Okay, before the question was, do you want to play? If you said yes, do you still want to play, or do you change your mind? Do you not want to play anymore? If you said no, did you change your mind? Now do you want to play, or do you still not want to play? So answer that to yourself and explain why to yourself. But think about this fact that you only have a 28% chance of winning. Alright, here's another example. You're playing a game of cards, okay? And it's your turn. You have to draw 2 cards, and you have to draw 2 kings in order to win the game. Now, there are 8 cards left in the deck. So here I have 1, 2, 3, 4, 5, 6, 7, 8 cards. And one of the kings has already been drawn in the game. So if you're not familiar with a deck of cards, there are 4 of each value in a deck of cards. So there's 4 kings, there's 4 nines, 4 fives, etc. So each value, there's 4 of them. Now, one of the kings has already been drawn. So if there's 4 in the deck and 1 has been drawn, that means there's only 3 kings left. Out of the 8 cards left in the deck, 3 of them are kings. Okay? In order to win, you have to draw 2 cards. It's your turn. You draw 2 cards, and both of them have to be kings. So what I want to know is, what are your chances of winning this game? And just as a side note, after you draw a card, it does not go back in the deck. Okay? So I'm going to draw a tree diagram for this one, but it's going to look a little bit different. If I wanted to, I could draw every single possible outcome of drawing 2 cards, but that would take a really long time, and it's going to get really messy, and my tree diagram is going to be really long, because there may be some kings left. We already saw there was a 9, there was a 5, and we don't want to find every single possible combination. All we're interested in is whether the card's a king or whether it's not a king, right? Those are the only 2 things we really care about. If it's a king, we're good. If it's not a king, it doesn't matter what it is. So, for my tree diagram, those are going to be my 2 branches. I'm either going to get a king, or I'm going to get something else. So I'm just going to write not a king. Now, what are my chances? Well, we know there are 3 kings in the deck out of 8 total. So my chances of getting a king on the first pick are 3 out of 8. What are my chances of not getting a king? Well, if there's 3 that are kings, the other 5 cards have to be something different. It's not a king. So that means you have a 5 out of 8 chance of not getting a king. Now, this is the probability on the first draw. Remember, we're not replacing the card. Once we pick a card, it does not go back in the deck. So the second time, we have 2 options again. If you got a king the first time, the second time, you could get a king again. Or you could get something else, not a king. Those are your 2 options. So our second branch is going to look the same as our first. And the same thing on the bottom. Now, what are the chances? What is the probability? What number goes here? Well, if we drew a king the first time, there were 3, we drew 1, now there's only 2 kings left. And there used to be 8 cards in the deck, but we already drew 1, now there's only 7 cards left. But if we drew a king, those other 5 cards are still in the deck. So we still have a 5 out of 7 chance this time, not out of 8, because we already took 1 card out. Now we have a 5 out of 7 chance of not getting a king. Same thing goes down here. The first time we didn't draw a king, the second time, there's still, those 3 kings are still in the deck, but there's only 7 cards left now. And over here, we've got 1 less card that's not a king, so we've got 4 instead of 5 out of 7 left. So we know on the first draw, the bottom of the fraction was 8, and on the second draw, the bottom of the fraction is 7 every time. So 8 times 7 is 56. So for every single one of these, we're going to have 56 on the bottom. To find the number on the top, we just have to multiply the two numbers on the top like before. 3 times 2 is 6. 3 times 5 is 15. 5 times 3 is 15. 5 times 4 is 20. We can change these to decimals. So here are our probabilities of each outcome. We have an 11% chance of getting 2 kings, a 27% chance of getting 1 king and 1 not a king, 27% chance of getting not a king and then a king, and 36% chance of getting 2 non-kings. Now to win the game, you had to draw 2 kings. So the only branch we're interested in is the one where you draw 2 kings in a row, and that was the 11%. So your chances of winning the game are 11%. You have an 11% chance of winning the game on this turn. If you don't, then you might have to wait till the next turn, or probably somebody else is going to win.